Welcome to the STEM Pathways podcast, where we delve into the fascinating world of science, technology, engineering, and math. I'm your host, Rohan Sharma, a passionate explorer of all things STEM. Each episode, we bring you captivating stories, cutting-edge research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we unlock the mysteries of the universe and explore the endless possibilities of STEM. Let's get started. Today I'll be interviewing Dr. Tsu-Jae King Liu, who holds a bachelor's, master's, and Ph.D. from Stanford in electrical engineering and is currently the Dean of the College of Engineering at UC Berkeley. How are you doing today?
Doing well. Thanks, Rohan, for inviting me.
And thanks for coming on the podcast. So to get started, I wanted to ask what made you choose your major of electrical engineering back when you were in high school?
Actually, I didn't choose this major when I was in high school. In high school, I was thinking about doing pre-med in college, and I went to Caltech for 1 year. There, I actually tried majoring in chemical engineering because that was the hottest field of engineering at that time. This was in the very early 80s. But I was actually dissuaded because the introductory course in chemical engineering had some partial differential equations that I had never seen before. And I thought, okay, this might be a little bit more than I can chew. Um, but I ended up transferring to Stanford University, and I decided to switch over to electrical engineering because it only had ordinary differential equations for the introductory course, but also because I had chosen not to pursue a pre-med um, a field of course of study because I found that I had no stomach for biology and organic chemistry, but I still wanted to find a way to help people. And I knew that electrical engineers made and designed and built devices that doctors use to diagnose and in hospitals and so on. So I thought that that would be a good alternative to a career in medicine.
Yeah. So what was your experience like while getting your bachelor's and master's degrees?
Well, bachelor's degree was interesting. This was in the early 80s. So at the time, there were not that many female students in the electrical engineering classes. And I actually, looking back, I don't recall any classmate that was female. So looking back, I didn't really engage so much with my classmates in electrical engineering. I did have friends outside of electrical engineering that were female, but they were in other majors. And so it was not really until I was getting close to graduation I realized, oh, maybe I don't know enough engineering to land a good job. I decided to take advantage of the 5th year, they call it co-terminal program at Stanford, where you can stay for 1 more year to earn a master's degree by taking more courses in your uh, selected field of study. So I ended up staying for an extra year to take more electrical engineering courses, and to help support that, I served as a teaching assistant. And as a teaching assistant, I realized I really enjoyed teaching. Um, and so when and I got to know some PhD students, including my husband. He was not my husband back then. But then that inspired me to stay on for a PhD. So that's how I ended up just staying at Stanford for many years to earn both graduate degrees. So it really was inspired by my desire to gain more technical depth, but then my love for teaching and discovering that research was also a lot of fun. And that's how I ended up earning a PhD and be on my career path.
Yeah. So I was actually talking to Asir Khan on the podcast recently, who's a postdoc at Berkeley, and I mentioned to him that you're going to be a guest soon, and he told me that Professor Krishna Saraswat, who I had on the podcast a little over a month ago, is actually your advisor.
Yes. Yeah, he's amazing. I think he only recently retired. It's set an outstanding example for me as a mentor and research supervisor. Very patient, gave me lots of time to explore, find my own path in research.
Yeah. Oh, can you talk a little bit more about what your PhD research was?
Sure. So I ended up working in a field called semiconductor technology. So semiconductors are the technology behind these computer chips. And at the time, I think a lot of the challenge was, okay, how do you fit more and more components onto a computer chip so it can perform more functions faster and at lower cost per function? And so my research for the PhD was really to find ways to help miniaturize these elements, which are called transistors. They're miniature electronic switches. So as part of that work, I uh, studied a material called it's a semiconductor alloy material called silicon germanium. So silicon is the primary, the predominant semiconductor material used today. But germanium was actually the original semiconductor material that was used to demonstrate the first transistors. So I studied an alloy of silicon and germanium to take advantage of the properties of silicon, the good properties of silicon, and the good properties of germanium together. And so silicon germanium thin films turned out to have a lot of interesting properties that could help to enhance the performance of integrated these computer chips, which we call integrated circuits.
Yeah. So next I wanted to ask you about what the Fin Field-Effect Transistor or FinFET is and what your contribution to it was.
Sure. So a transistor is a miniature electronic switch, and there are today up to 100 billion transistors on a single chip, which is maybe the size of a postage stamp. In order to have that many transistors fit into such a small area, they have to have very small dimensions. And it turns out that when you make a transistor really small, it's difficult for it to turn off properly. And so the fin-shaped transistor, which is called the FinFET, FET stands for field effect transistor. So you apply a voltage to induce an electric field to turn on and off that transistor. So we at Berkeley, my colleagues, faculty colleagues, and I studied different ways to have a transistor have more than one control electrode. So a transistor has a control electrode that determines if it's on or off. And ordinarily at that time, the control electrode just laid on the surface of the semiconductor. So when you apply a voltage, that induces an electric field, and that makes the semiconductor either conductive or not. Now it turns out when you make that semiconductor really the transistor really small, it's hard to avoid, like when the transistor is supposed to be off, some electrons from sneaking around the gate, the control electrode, and just causing leakage current. So we came up with a fin-shaped semiconductor. So if we could actually pattern the silicon to form tall and narrow fins like the back of a shark, and we wrap the control electrode around it. So think of it as, let's say you have water flowing in a hose, and you want to pinch it off to stop water from flowing. You can press from one side, but you can actually turn off stop water flow if you can pinch the hose from two sides, right? Like this, rather than like this. So that's the concept. We want to be able to wrap this control electrode around the semiconductor. And the easiest way was to make the silicon a fin. You can just wrap the control electrode around it. And it turned out that innovation has allowed the semiconductor industry for the past dozen years or so to continue to shrink the size of the transistor to fit more and more of them on a computer chip, so that these computer chips can now perform a lot of functions. This provides for more computational ability for reasonable, affordable cost. So that was the innovation.
Yeah. So how has semiconductor research evolved over the years? And what major advancements are happening right now or that are going to continue Moore's Law?
Yeah, good question. So Moore's law is all about fitting more and more transistors into a integrated circuit package. Um, so today there are some fundamental physical limits to how small you can make a transistor and still have it turn on and off properly. Even if you can turn on and off properly, maybe when it's on, it's not going to conduct as much current when it's that small. So to overcome these fundamental physical limits, we can innovate with new materials. So maybe alternative semiconductor materials that can conduct more electricity more quickly. Germanium turns out to be one of them. You can have even more advanced transistor structures that are more complex to fabricate. So companies like Samsung and Intel, and eventually TSMC have already started to introduce even a more complex transistor structure that can provide more current even though it's small. Now, it might not be cost effective to make these small transistors and cram them all together on a chip anymore, because it's just too sophisticated manufacturing process to be cost effective. So now industry has gone to stacking chips, these computer chips on top of each other in a compact package in order to fit more and more transistors in a package rather than more and more transistors on just a single surface. Um, so we will continue to see improvements in computing performance because we're continuing to improve the level of integration in a package, but rather than shrinking a transistor, we might be stacking them and using new materials. But all of these innovations require a lot of problems, practical problems to be solved. And this is where we need engineering innovation, new materials, new manufacturing processes, and new chip design. So maybe chips, the circuits can be designed to operate more efficiently with. So how can you get more functionality out of a single transistor? That's also a new way to innovate by coming up with new computer architectures. All of these together will allow the industry to continue to improve the computational ability to meet the demands of AI and machine learning. That we need the best and brightest students to come and help us in this endeavor.
Yeah. So what has your lab been researching right when you started as a professor, and what's it researching now?
Uh, when I first started, because in my PhD I had worked on thin films of silicon germanium, I ended up working on thin film transistors. So transistors that you can, where you form the semiconductor as a thin film on top of some substrate. And I worked for a few years at the Xerox Palo Alto Research Center, Xerox PARC. Um, and there, back then, Xerox was known as a copier machine company, right? And you make photocopies, you print out things on paper. So Xerox made printers and photocopiers, and they saw the digital revolution coming. And some of the researchers there said, well, in the future, people will want to look at their documents on screens that are more like flat, like paper. Back then, the early 90s, there were these large cathode ray tubes. So TVs were big and bulky, if you remember. And these laptop computers, like there's no display that was portable like that. Computer monitors were big, bulky devices. And so Xerox had researchers work on flat panel displays, which are like everywhere now, right? Your cell phones use flat panel displays, your laptop computers, your iPads, um, computer monitors, and even TVs are flat panel displays today. So back then at Xerox PARC, we were working on flat panel display technology. And it turns out in a display, every single picture element or pixel, the brightness is controlled by a transistor. And that's a transistor that's formed on glass. It's not formed on a semiconductor substrate like computer chips are. So you have to form the semiconductor for the transistor as a thin film, right? So thin film transistor technology was critical to develop high performance thin film transistor technology was critical for enabling today's flat panel display technology. So that's what I worked on at Xerox PARC. And then when I moved into a faculty position at Berkeley, I continued to work on thin film transistor technology. And I think some of that work has actually been realized or that technology is used in displays you have in your cell phones and your laptops and TV monitors and so on today. But in the United States, the federal government that funds this research, they decided, well, in the future, we can just buy flat panel displays cheaper if they're made in Asia. So research funding kind of dried up for thin film transistors. And so that's why I ended up going back to doing research on conventional, computer chip transistor technology. And that led eventually to the invention of the FinFET.
Yeah. So what year did you start as a professor at Berkeley?
Pardon me, what do I do as a professor?
Or what year did you start as a
Oh,
professor?
what year? I started in 1996.
How has Berkeley outside of academics changed over the years?
Outside of academics. Okay. Well, Berkeley, the University of California at Berkeley, the size of the student population has grown tremendously, and also the diversity of the student population. California, if you look at the diversity of high school graduates in California, they're quite diverse. And so there's a lag, but so it's not surprising that since most of our undergraduate students are from California residents, the diversity of students has increased. And so over time, we've adapted our methods for teaching and mentoring students to make sure that we can better support the diversity of students to succeed in their studies here at UC Berkeley. And over time, this means that we've paid more attention to excellence, not only in research, but also in teaching.
And then one other thing I wanted to ask is how this whole tech boom, like across Silicon Valley, has affected Berkeley.
I think, well, first of all, Berkeley researchers, alumni, and faculty alike, we've all contributed to the tech boom in Silicon Valley, whether or not it's the innovations that we come up with through our research, or our students who graduate and work for the companies, or faculty and alumni who start companies, the whole industries. So Berkeley has contributed tremendously to Silicon Valley. Maybe traditionally we didn't brag about that so much, but nowadays we've actually developed quite a rich ecosystem for entrepreneurship at Berkeley. So we have programs to provide seed funding to students to help them start companies and to faculty as well. And we have a strong network of investors as well as experienced entrepreneurs who provide mentorship. So I think Berkeley has definitely contributed to the vibrant entrepreneurial ecosystem in the Bay Area. But of course, we've benefited from that as well, because then those companies give back and fund research at Berkeley. But also, I think a lot of people do give back and provide like funding for scholarships, and that really helps to support a greater diversity of students. We are known as an engine of social mobility. Students who come to Berkeley, it's surprising. I think it's like more, at least 40% of our students are qualified for Pell Grants, right? So financial aid. And actually, I think it's like 40% of students at Berkeley actually don't pay tuition because, for financial reasons, they get the financial aid. So I think being part of a vibrant ecosystem benefits our students, because then a lot of them, we can increase accessibility of our programs to a greater diversity of students.
Yeah. So how long have you been the dean of the College of Engineering for?
Well, this is my 7th year, so I've completed 6 years, and yeah, I'm now just near the beginning of my 7th year.
So what do
I
you do
think
with
that's
this
the
role?
lucky year, right?
Yeah. So what kind of things do you have to do with this role?
So as dean, I mean, I'm still a faculty member, and so I still have a research group, although it is smaller because I have less time on research. As dean, a lot of my job is to raise awareness and resources for the college and its departments, and we have a number of academic institutes and centers to broaden the range of learning experiences for our students. So a lot of it is just raising funding for supporting our faculty and students so that they can all thrive. I mean, that's our goal here. I view my job as supporting our faculty and our students to succeed in their academic endeavors, and that's very rewarding because if you can help others achieve more than they originally thought was possible, that's really making a real impact, and that's what makes the job of being a dean very rewarding.
Yeah. So one thing I wanted to ask you about was I saw a talk that you did where you talked about EQ in AI and how important that is as we move forward. What
Ah,
are your thoughts on that?
yes, that was a talk I gave a number of years ago. So, um, I think, AI, just like any new technology, can have tremendous benefit for people and for humanity, right? But as is the case for any new technology, it can also potentially have negative impacts, right? Unintended negative impacts. So I think it's really important that the people who design and build new systems like for AI are fully aware of the, the the benefits, potential benefits, but also potential harms of their technologies. And everybody has blind spots, so it's really important that we include a great diversity of perspectives in our engineering innovation teams, so that we don't overlook something. So a common example is the airbag systems that are used in cars today to protect people in case of a crash. Those systems were developed initially for men, for adult men, and actually Caucasian adult men. And so, after many years of looking at crash data, I mean, real statistics, the industry realized, oh, well, women and children, people who didn't fit the physical profile of a Caucasian adult male, tended to get more injured, a higher rate of injury and deaths due to airbags deploying. And then it's like, okay, then it took almost 20 years for the government to mandate that when airbag systems are developed, the dummies, the crash test dummies used had to also include dummies that represented different body types and shapes. Now it took 20 years, and lives were lost, and lives were dramatically affected. I think if we had more diversity on the engineering teams that designed the airbag systems in the first place, maybe all these loss of lives and injuries could have been avoided. And so AI, same thing. If we don't have a diversity of people working in teams to develop these systems, there might be something that people overlook, and you don't want to wait until AI systems cause a lot of harm before you go back and try to fix it, right? So that requires emotional intelligence as well, because to work collectively with a group of people who have different ideas, different perspectives, different lived experiences, you need to get along with them, be open to their ideas, be open to their constructive feedback, be open to communicating your feedback. And if you don't get along with people and collaborate effectively, then that means you don't have, this is where emotional intelligence is needed. Then you're not going to have as effective a team. And so I think this is why it's all the more critical nowadays, of diverse teams of engineers. And this is why it's really a good thing that we're seeing a greater diversity of students pursuing STEM degrees and particularly engineering careers.
What kind of changes have to be made to increase diversity in STEM, specifically in engineering, ranging from all the way in kids who are like not even 10 years old yet, all the way up to the higher levels of academia, and even into people who are already working in their jobs?
Well, there's probably multiple ways we can increase and support diversity in STEM and especially in engineering. One thing is we can do a better job of communicating the importance and impact of engineering. Like if people, the average 8 to 10-year-old, are they aware that engineers actually design and build devices, systems, processes that people depend on today? And it can help make life easier, more joyful, more sustainable. I think we need to communicate that engineers, essentially, we design and build the future. The If you think about it, we're being interviewed, or we're talking now using devices and systems designed and built by engineers, and that changes the way that we live, work, and play. Imagine that today's engineers are going to be transforming the way we live, work, and play in the future, and it's rewarding to see how you can improve quality of life for other people. But it does it. I think it does require that we can, attract and support and work together with a greater diversity of people. Because ideally, we want the things that we design, right, our products, we want them to be successful and be used by everyone, right? We don't want to design products. No company wants to design products just for like one small demographic, because you're not going to make as much money, bottom line. But you won't have as much positive impact unless you think about more broadly that what you do ultimately, how does it relate to people? How can it better serve people and society? I think we need to get that message across to the public that engineering actually is all in service or to benefit people and society. And I think that in itself can attract a greater diversity of students and people to engineering.
Yeah. Are there any things being done at Berkeley to help promote this?
Well, I mean, we definitely recognize as we have a greater diversity of students, they come from different backgrounds. So we want to be able to adapt the programs or the resources we have available to support student success to each individual student. So we have programs like mentorship programs, so that every student who wants one can have a mentor, whether or not it's a peer mentor or an alumni or a graduate student or a faculty member. We have programs to help students improve their communication skills, help them to cultivate leadership skills so they can gain confidence in speaking and leading people. So I think all of these soft skills, coming back to the topic of emotional intelligence, those are the things that I've been really trying to support as dean, because I know that those skills are going to ultimately determine how successful our graduates are in their career path, no matter if it's engineering or in business or in medicine or in politics, right? If you can't get along and work well with and lead other people, then you'll be less successful in your career.
Yeah. So you're also on the board of directors for Intel. I wanted to know how you even got into this position in the first place and what you do in this role.
Good question. So when I was a student at Stanford, a PhD student, one of my mentors was, in addition to Professor Saraswat, was Professor Jim Plummer. He was actually the PhD advisor for my husband, and so he's been a wonderful mentor. He was a dean of engineering at Stanford for many years. I think it was more than 10 years, and accomplished a lot. So he was actually on the board of directors for Intel, but they have a rule eventually, if you reach a certain age, then you have to retire. And so when he knew that he was coming close to retiring off that board, he recommended me, and I was interviewed, and that's how I ended up joining the board of directors at Intel. But of course, my area of expertise, right, semiconductor devices, being a co-inventor of the FinFet, which Intel was the first to commercialize many years ago. Of course, my technical qualifications were part of the reason that I was chosen for to serve in that role. But it also demonstrates how important or the value of a network, right? For students, the people your fellow students, your teachers, your professors, your mentors in the future, they're all part of your network of people and that who can help you, and you can help them over the in in your throughout your life. So I've been grateful and fortunate, and I'm grateful to have these people in my network who have been the outstanding mentors, but who have opened doors for me. Um, and I've likewise tried to do the same thing for other people, of course, in my network. But I think you never know who can help connect you to new, exciting new opportunities. So as a rule of thumb, I think it's just never hurts to be grateful, express appreciation, and be kind to other people. Um, you know, people, if you are the kind of person that likes to help others, then it's not hard to imagine that other people will be happy to help you when they have a chance.
Yeah. So what are some of the things you do as a member of the board?
Hmm. So the board of directors for a publicly traded company has a few responsibilities. Of course, they help to oversee the strategy for the company, the business strategy. They help to make sure that the company is following the rules and regulations for public companies. Um, Also, they're responsible for the hiring and the CEO, right? So that's interesting. But the ultimate, like we are beholden to the shareholders, right, to the owners of the company. So our job is to help to ensure that the company's leadership makes the good decisions that will ultimately benefit the shareholders. In other words, long term, ideal, short term and long term success of the company, so that shareholder value increases. Ultimately, that's the role of the members of the board of directors. But serving in that role, I've learned a lot about leadership, including engineering leadership, and whatever lessons I've learned, I've tried to support new programs and initiatives at the university to better prepare our engineering students to be more successful leaders in the future.
So for my last question, I wanted to talk a bit about a book you wrote. It's called Electrical Engineering for the Curious High School and College Student. Why Study Electrical Engineering? The
Yes.
Undecided Student's Guide to Choosing the University Major and Career Path. So this is the exact reason I started this podcast. And the question I always end off with is what's one piece of advice you'd give to someone who's still in high school or college wanting to follow your career path? So what are the biggest takeaways from this book, and what's your biggest piece of advice?
Okay, actually, it's been so long since I've contributed a chapter to that book. I don't remember at this point what the pieces of advice I gave are. But I think looking back, I think no career path of anybody who's successful that I know have known is straight. So I would say don't worry about always succeeding, and you just continue to learn. Like if you love learning, then you will succeed in life, because no matter if you succeed or you fail, you'll well if whenever you fail, that means, well, there's an opportunity to learn. Just like anything in life, right? We practice and get better. So I think the key piece of advice would be, don't take failure as a sign that the this field or whatever you're trying is not for you. Just learn from your failures, and grow from grow from that experience. Think of failure as feedback on how you can uh, improve, or maybe gain some new knowledge that you didn't have before, and try again. I mean, and that's the point of research, right? It's it's coming up with new solutions to problems that people hadn't solved before. And if everything you try always works the first time because it works, then it wouldn't be called research. It would be called search. Like you search and find the solution because you know it exists. Now, research is about trying and trying again, because you try something, it doesn't work, figure out why, and then try the next time with an even better idea. So that's just the way. If you want to succeed in life, think of life learning as a lifelong process. So in college, in graduate school, the main thing that students take away is learning how to learn. If you embrace learning and this growth mindset, you will you will you will succeed in your career path.
Thank you again for that great piece of advice and for joining me on the podcast.
You're very welcome. Thanks so much, Rohan.